All right. Okay. So let's get started. Today we're going to have two lectures pretty much talking about various structural properties of the networks. Nothing fancy, but can be quite helpful. So on the previous lectures, first of all, we talked about global statistical properties of the networks, right? We talked about degree distribution. And again, in all this type of networks, what do we know about the degree distribution? What function does it usually follow? Power law. Yeah, it's power law distribution. Then we talked about path length and average path lengths, and what do we know about those networks and the path lengths? What's the property of those networks? 6 degrees of separation. What do we call this? It's small world, right? A small world. The fact that the diameter of the network on average might grow as a logarithm of the number of nodes. So they're very tightly connected. And then we talked about clustering coefficients, and we saw that in real networks, it's pretty high. But those are properties of the networks, right? So you take a network and you calculate the properties of the network. Then we talked about and that's global, right? Statistical properties, definitions, the description, statistical description. And then we talk about local properties, properties that you can associate with a particular vertex, right? And in fact, this local clustering coefficient is a property that is related to a vertex because it's computed per vertex. And then probably, the most important properties were node centrality, which is the location of the node with respect to other nodes and connectivity patterns around the node. And by the way, what kind of node centralities do you remember? It's a test, quick. Cut centrality? Okay, well, what's the Eigenvector centrality? But the easiest. Degree centrality, next one. Between the centrality and closeness. Closeness. Okay, so degree, closeness, betweenness, these are the easiest centralities, right? But then, you go further, there's a cut centrality, then you go further, there is Eigenvector centrality. And then we talked about Pagerank, right? So how is Pagerank different from Eigenvector centrality? Oh, come on. So Pagerank, first of all, designed to handle situation when you have a directed graph, right? When you have direction in the edges. And typically, usually, the original centrality metric, Eigenvector centrality, will fail there. You will not be able to compute. It's one thing. The other thing is Eigenvector centrality is just built on the assumption or from the idea that centrality of the node actually depends on the centralities of the surrounding nodes, right? And that's pretty much the only thing that comes into it. While when we talk about PageRank, we talk about this random walks on graphs, and there is a particular probability distribution. There's a particular way how you compute it. Now, we talked about PageRank for directed graphs, but we also talked about one more metric, one more algorithm. I know it was like 3 weeks ago, but still. The algorithm that assigns 2 numbers to every node. Oh, come on. Hobbes authorities. It was hits, right? Remember? Or we kind of have like rotating audience here, right? Some people come this week, other people come in another week. All right, so if you don't remember, please go back into the lectures. They're online. Take a look, read it, refresh it. So anyway, when we talk about centrality, there is this very simple geometric centralities, and then there is the stories about Eigenvector centrality, PageRank centrality, Hobbes authorities. Now, one more question. When we talk about this very simple metrics like degree centrality, that is really only about local neighborhood, right? And when we start talking about Eigenvector centrality, PageRank, it's more about the global structure of the network. But still, it is a property that is being assigned to a vertex. So what we're going to do today, we're going to talk about pairwise properties. So when you have like 2 vertices, right? If we can compare them, can we compare them? How can we compare them? How can we compare them based on their position and role within the network. And then we talk about correlation between the values on those vertices. And you know, we'll talk about what's called authoritative and disassociative networks. So the very first definition is a definition of structural equivalence. We call two vertices structurally equivalent if their connectivity patterns coincide. In other words, if two nodes have the same incoming edges and the same outgoing edges. So if you look here, let's say this node and this node, they both have only outgoing edges, and there is this one edge comes to V1, this one edge to V2, and again V2 and V1. So from the connectivity pattern point of view, they're indistinguishable, right? They have exactly the same connectivity. What other nodes? And so these two nodes, based on this definition, are structurally equivalent. In fact, when the nodes are structurally equivalent, the rows and columns of the adjacency matrix will be identical, right? Because those rows and columns, they encode connectivity. So if you take a look at the node U1, and then this is a row, and node U2, this is a row. So this is outgoing links, outgoing edges. And of course, those two vectors are identical. And the incoming both are zeros because there's no incoming links, right? So very simple, you know, two nodes structurally identical if they have the same rows and columns in the matrix, or pretty much if the connectivity pattern is the same. So that's very easy. Now, with this definition, we run into some troubles and some sort of contradiction. Where do you think the problem could be with this definition?
If we have two nodes and they have edge one to another, they're
Yep.
actually structurally the same.
Yeah. So if you look at the node V1 and V2, they're pretty much their connectivity pattern, except for the fact that they're connected to each other, is identical, right? So if you think about the definition and think about the fact that they're playing exactly the same role in the graph, they should be structurally identical. But then if you look at this, you know, they're not, because this is not connected to this one, this is not connected to this one, right? Or if you look at the matrix here and there, there are different patterns. So, you know, in order to use this definition, so there are again, in this science, there are different ways to handle it. One way is to say, okay, well, this is a structural equivalence, or another way to put it, strong structural equivalence. This is a definition, and so according to the definition, these are not equivalent. Not very convenient. What people do instead, they try within the definition to fix this situation and say, like, okay, you know, in order for these two nodes be equivalent within this definition, we can create or add edges that point to themselves, right? To create self-loops. In terms of the matrix, that really means just you put ones on the diagonal. But now if there is a one here, there is a one here, which means there is a self-loop and self-loop. Then, of course, those columns identical, rows identical, so they're equivalent by the definition. All right? So people play different tricks. Sometimes you can say, well, look, this is a definition, so then these are not equivalent. Sometimes they say, look, let's correct this and assume that every node has a self-loop. And then we don't have this contradiction. Okay?
And if we add loops, what about the U1 and
Oh, that's fine. Oh, that's fine. So you add self-loops. It's actually a very good question. You add self-loops only to those where you have this issue, right?
not just no?
No, not to this, right? Because if you do this, then if you do this, you'll get one, for example, here and one here, and then you break the definition. And as I mentioned, so the original then definition quite often called strong structural equivalence, and then we have self-loops for adjacent vertices. And so that sort of relaxes the definition and makes our life easier. But when is this useful? Well, if you look at these pictures, for example, which nodes here are structurally equivalent. If you look at this one, which nodes are structurally equivalent?
All except the center.
Yeah, so pretty much all of these nodes are structurally equivalent because they have only one connection to the central node, right? Here, which nodes? Well, if you look at these two nodes, right, they have the same connectivity pattern, and these two nodes have connectivity pattern the same, right? So, and these two have the same connectivity pattern. So which means these are equivalent and these are equivalent. Here, every node is structurally equivalent to any other node. So in some sense, it's sort of the notion that you can replace any node with any other node. This actually has interesting consequences if you think about if, for example, the graph reflects some sort of processes within, in manufacturing processes, or maybe some social structure in the network, then it really means sort of one of those friends is equivalent in terms of the connection to the other friend, and so you can just easily replace one with another, right? Well, in some sense, imagine that you want to reach somebody, and there are two friends who know this person. Well, for you, it sort of if leaving everything aside, if the only purpose is to reach this third person, right? It doesn't matter. And so that's what's sort of behind the structural equivalence. Now, in real life, most of the time, you don't get this sort of nice pictures like here, where it is very clear, clear connectivity patterns, identical connectivity pattern. Most often, you will get something like, for example, let's look at this node and at this node, and there is some overlap in terms of the neighbors, right? But then there are more neighbors, there are more nodes this guy is connected to, but they're not overlapping. So the neighbors from this node and this node do not overlap. So they're not structurally equivalent, but there is still sort of some feeling, right, that they are structurally somewhat similar. Well, because they have this overlap in terms of their neighbors, and it feels like they could play sort of similar role within the network. Give or take, right? Not exactly structurally equivalent, but similar. So what kind of definition can we come up with? If you want to be able to characterize, because like, say, I want to be able to characterize this, or talk, let's say, compare this node, and maybe let's say this node, and let's say this node, and this node. Can I do that? I want to compare based on the connectivity patterns.
How many neighbors, equal neighbors do they have?
For example, right? So I can calculate how many neighbors in common they have. But then if I just do that, I just calculate number of neighbors in common, then I might run into issues with the size of the node, right? The larger nodes might have more neighbors in common than the smaller nodes. And so then your metric will be biased toward the size of the...
Proportion.
Yeah, so you want to do proportion, exactly. So what you want to do is you want to take the total number of the node degree, which is the total number of neighbors, and figure out what is the proportion of neighbors things overlap. So formally, yeah, it's actually called Jaccard Similarity, right? So what you do is you take the neighborhood of one node, neighborhood of the other node, find the intersection, right? So those nodes that overlap, and divide by the total number of nodes for both of them. But this is a union, right? So you don't double count. Make sense? Okay, so you can do that. Now, the only trouble with this approach, there is a caveat here. What is it? Like when this wouldn't work? Or, okay, maybe work, but will not be as precise as you might want it to be.
Some kind of graph without edges, sparse graph.
No, that will work. I'm not talking about like sort of the technical way of, not about the ways of computing it. It's more conceptually. Imagine that you have a weighted graph, right? You have weight on every edge. Let's say the weight corresponds to the strength of your connection with, or it's a friendship graph, the strength of your connection with other person, right? So then, all of a sudden, your notion of equivalence or notion of similarity should also include the strength of the connection, right? So the edge weight. And this one does not include it. And so the way to do it is actually introduce or use what's called cosine similarity, right? Like in any high-dimensional vector space, where this will be the vectors that represents our nodes, right? And then you just normalize it. So it looks like cosine dot product. And if you think about the matrix notation, that's how you calculate it. Now, this works. This makes sense for undirected graphs. When you have directed graphs, you have to be more careful, right? Because then you can distinguish incoming and outgoing edges. Finally, there is yet another approach you can use is Pearson correlation, which is sort of typical correlation coefficient. So what you do, you just calculate, actually the correlation coefficient between those two nodes, thinking about as data points, and just use, the matrix to do that. Right? Honestly, most of the time, people using this Jaccard similarity. If you have weighted graph, that's what they typically do. Right? But one thing, and you will see this more and more within the story, that you can actually take a lot of statistics and a lot of measures you use typically within data science and map it onto networks by just doing calculations in between nodes that are connected. And we're going to do it on the next slide one more time. Any questions about this?
Can you just say what vectors actually represent here?
Oh, vectors represent, this is a vector. Vectors represent the columns or rows of the matrix. If the matrix is, if the graph is not directed, then their matrix is symmetric, and then it doesn't matter whether you take columns and rows. If a matrix is directed, then when I'm saying you have to be careful, because then the rows and columns will be different, and so then you need to start thinking about, okay, it's structurally equivalent in terms of incoming or outgoing edges. But that's just, and the matrix, it's adjacency matrix, the Aij matrix, it's this one. Okay? Make sense? All right. Let's move on. Now, actually, if we still want to use cosine similarity, we can do that even for unweighted graph and unweighted undirected graph. Then computations actually simplifies, and we can look back into the formula for a second. There is this aik akj, right, and you sum over all k's, which really tells you it's just you go from node I to node k, and from node k to node j, and sum over all k's, right? So it's one node to another node through intermediate node. And so if those guys are just zeros and ones, if it's a binary matrix, which means unweighted matrix is just a connectivity pattern, then the sum is just equal to the number of shared neighbors. Oh, because again, you go from one node to another node through intermediate node. And you calculate all those paths, which is length 2, which means the number of those paths is the number of nodes that overlap in the neighborhood of those two nodes. Does it make some sense? Yeah? So if you need to go from one node, it would be good if I could draw. If you need to go from one node to another node through the intermediate node, you do it in 2 steps. 1 step, 2nd step. Then if there is another path, 1 step, 2nd step. If another path, 1 step, 2nd step, right? So I just drew like 3 paths, but that means there's only 3 nodes that are overlapping in the neighborhood of those 2 guys. So that's what this counts. So it's number of overlapping nodes, and then you can actually, the cosine similarity becomes Nij divided by square root of Ki and Kj. So it's slightly different from just Jaccard coefficient, but sometimes it actually works better. And Ki, Kj, these are node degrees. So you're also pretty much calculating very similar thing. Number of overlapping nodes divided by node degrees, but here it's square root of them. So it's slightly different than Jaccard, but also usable. Typically, when you try to use those things in practice, you kind of compute both of those metrics. And then you try to figure out which one works better for you. Very often, like in linear algebra world, it's just faster to compute, simply because you do matrix multiplication versus counting common neighbors. So very often, that's the one you will see in practice. And you can also calculate Pearson. So now, here is something I want you to notice. This is a graph, and this is the same karate graph we have been looking at for a long time. What we have on the right, I typically used to show graph and then adjacency matrix. This is a graph and node similarity matrix. So what it means is what we have is a color-coded similarity measure. So this cosine similarity coefficient, this one, we calculate for every pairs of nodes. So since it's a matrix, right, so there's one node, another node, that's the color is a similarity. Of course, every node is self-similar, so diagonal is dark. But then there are groups of nodes that are more similar than among themselves than others. And so we can see here a couple nodes quite similar. Then there is these two nodes quite similar, and in terms of their connectivity patterns. And I think this one is it's probably, I think it's numbered 1 to 3 to 34, and this is like 33, 34, and they have very similar connectivity pattern. You can actually see it even here, and so this one, those two nodes will be. The matrix will have dark colors, right, because the values are large. All right, so again, important here, this is not an adjacency matrix, right? This is not a connectivity matrix. This is a matrix that counts the similarity between two nodes in terms of the overlap of their neighbors. Make sense? So if you, for example, want to simplify your graph and throw away nodes that are duplicate in terms of their importance to the graph, right? In terms of their structural properties, you just find out those that have dark colors here and just get rid of one of them. So in some sense, it's very similar to if you have data matrix and you have data points that are correlated, right? Then you can actually create correlation matrix. And if you want to have subset, you want to have a data set that are smaller but has the same properties, you can remove those data points that are correlated, right? So that's the same idea. Okay? It's a correlation matrix built on their connectivity pattern of the graph. Yeah, I don't see any excitement or any like, yeah, we understand, nah, we don't know. Does it make sense? Oh, okay, all right. Does this make sense? All right, good. Because you'll have to do it in one of the homeworks. So, just so you know. All right, let's move further. We talked about the sort of structural equivalence where we took into account only the nearest neighbors, right? We're saying the nearest neighbors are identical. The overlap, we overlap on the nearest neighbors. That's how we define similarity. But then we can say, like, wait a minute. We pretty much done very similar exercise when we talked about centrality, right? We said that first we started with like the node and its neighbors, but then we said like, oh yeah, maybe centrality can be defined as the centrality of the node depends on the centrality of the nodes that are connected to this guy, right? And their centrality depends on the nodes connected to those nodes, et cetera, et cetera. So maybe when we talk about equivalence or structural equivalence, and in fact, now it's called, what we're going to talk about is called regular equivalence. We need to take into account like all the nodes in the graph and all the patterns, right? All the connectivity in the patterns in the graph. And the idea is exactly the same as with eigenvalue centrality, which is, all right, if I want to define centrality, equivalence between nodes I and J, and they're connected to other nodes, well, we'll calculate this equivalence through the equivalence between their neighbors, right? So if these two nodes, we're going to talk about them as being similar or equivalent if they're connected to the nodes that are also equivalent. So you realize we're actually doing this sort of circular sort of thinking again, right? We're saying these two equivalent if their neighbors are equivalent, right? So the node is central if the neighbor is central. But now we're talking about pairs of nodes. They're equivalent if their neighbors are equivalent. A node, of course, any pair of nodes can have a lot of neighbors. And so then we need to go through all the neighbors and see if they're equivalent. And then just doing it recursively. Now, there's a slight problem with this definition because it's obvious that if you take here, for example, I sub I, so which is equivalence of the node to itself, it would make sense within the definition that it is equal to 1. I mean, node should be equivalent to itself. That doesn't work with this formula, so the formula has been just corrected manually by adding here sigma ij that forces this to be 1 or a little bit greater than 1 when it is, when it is the node itself. And and then you can calculate this recursively. Some people use it, some do not. Again, if you kind of compare this to the web, right, you might find this definition of regular equivalence, of the nodes being equivalent. Or you might find slightly different definition. It's also sometimes called regular similarity, regular equivalence. Guys, one just sort of comment is we do get within this network science a lot of definitions that are kind of close to each other but not identical, right? For the situation which is very similar to each other, because there are a lot of people working, and they come up with their own sort of names, algorithm definitions, right? Publish a paper, bring it to attention of scientific audience, right? And some people accept it, some others do not. And so what you quite often get is two very similar definitions, but slightly different. That's exactly what happened with the clustering coefficient. That's what's happening here. And there are a group of people that want to use this and say this is the right way. There are other group of people who says the previous definition is the correct definition. Let's use that. And you'll see both of them in the scientific papers. Maybe like in 10, 15, 20 years when this science becomes more mature, one of those definitions survives, other disappears, and then it kind of will be straightened out. But for right now, there is always, there is a sort of, always different ways to describe the same thing, and they're not, identical. Make sense? So there's this sort of this, if you notice, I didn't put here the name. So this is sort of one guy is proposing. Here is yet another group of authors who proposed in 2006 the following definition of similarity, or again, equivalence of the nodes. The idea is that we calculate equivalence between nodes I and j. Vertex j is similar to vertex I if it has a neighbor that is similar to this vertex. So I and j are similar if one of the neighbors, if it has a neighbor that is similar to j. So it's slightly different twist on the previous definition where we looked at the pairs, and here it says these two guys similar if this has a neighbor that is similar to this node. And then you write sigma ij, the similarity. This is also your step to your neighbor. This is similarity between the neighbor and this node, and also this delta ij thing to force sigma ij to be 1 when you calculate similarity to itself. Now, the advantage of this approach is that this, if you look on the previous definition, this is quadratic in terms of the matrix. So it is harder to compute. This one, it is linear with respect to the matrix. So you can take this equation and write it in the following way, and there's a closed form solution, closed form answer to it. So you can just, take this matrix, invert it, or solve the linear equation and get similarity, this type of similarity between all the pairs of the nodes in the graph. In the previous story, in this situation, you actually need to do recursive computations and hope it converges. So, which one is better? I don't know. People use both, and they give slightly different answers. But they have the same feel in the sense that the similarity between nodes depends on the similarity between its neighbors, right? And so there are two nodes more similar if their neighbors are similar, or they're connected to similar. And this whole story is really about the role of the node in the graph, right? So if you want to find the nodes that are, as we started, equivalent, or here we move to this idea of similarity. All right? Now, as we've done before, this works well, what I just described is defined and works well for undirected graphs. Now, so the same as eigenvector story. Now, for directed graph, we had PageRank. Here we have slightly different method. Chen and Widom, it's a paper 2002. But again, the idea is very, very similar. It's just slightly different normalizations. We're saying that two nodes are similar. The similarity between two nodes is defined through similarity between their neighbors. So you take a node, you have two nodes, A and B. You take a node A, you take all the neighbors of this node, take a node B, take all the neighbors of the node, go over them, find the similarity between all the pairs of neighbors in between, that they have, normalized by the size of this neighborhood, and do this iteratively. And the authors shown that this approach, in fact, for directed networks, well, and then for undirected too, will actually converge. So this thing will converge, but we need to do, there is no, one-shot solution. This is quadratic, so we need to do iterations to get to the convergence. Again, very simple to very similar to eigenvalue stories. And in fact, you can also show that depending on eigenvalues, this thing going to converge slower or faster. Now, going back and mapping it into what we started with, the story is, notice if there is a if there is a direct there is a direct overlap in between neighbors, we can talk about structural equivalence. Here, we don't necessarily assume the direct overlap in between neighbors of a neighborhood of the two nodes. So this node can be here, this node can be here. And we define their similarity based on similarity between their neighbors. There's not necessarily overlap. When we talked at the beginning of the lecture about structural equivalence, we talked about about overlap of the neighbors, right? So for that structural equivalence to be greater than 0, the two nodes should have a path between them, at least one path of length 2, because they need to have a common node in common, right, in their neighbors. If they do not, then the structural similarity is 0. This one talks about similarity. It doesn't matter where they are within the graph, right? It's the similarity between them is defined through, through the similarity of the neighbors, of their neighbors. Makes some sense? Sort of, kind of. But you feel the difference between that structural story, the structural equivalence, and the similarity, or not? Yes, no, yes, no. It was kind of weak, yes. All right, again, one more time. When you talk about structural equivalence, you have one node, you have its neighbors. You have another node, it has its neighbors, right? Now, if they're far away within the graph, there is no overlap in between the neighbors, that structural equivalence is 0. Now, if they're close enough and there are some neighbors that overlap, you calculate that overlap, and that's how you calculate structural equivalence, right, or structural similarity. Now, in another story, you can take two nodes somewhere far away within the network, or close, it doesn't matter. And it doesn't matter whether neighbors overlap or not overlap, but you say there is those two nodes structurally similar, or like regular equivalent, or the sim rank value, or you calculate that value based on the similarity between their neighbors. So neighbors can be similar, not necessarily overlapping. Structurally similar. Okay, well, let's assume that you captured the difference. Then go through the slides, it might become more clearly. But again, the idea is when there is an overlap, it's very easy to define things. When there is no direct overlap and the nodes are far away, you define their structural similarity through the similarity based on the similarity of their neighbors. And that's why it sounds, this recursive loopy definition sounds very much like, eigenvector story.
And in neighbors,
Yeah, the neighbor, I'm sorry, say it again?
In neighbors have their edge to A or B. So what actually in neighbors means?
No, in neighbors, okay. Now, in neighbors, it's just meaning, so this thing is, if you notice, it says it's directed graph. So in neighbors, for this definition, means your direct neighbors, which means one step away, but the edge points to this node, like in PageRank definition.
So A points to this.
Yes. So the guys in I of A points to A. I of B points to B. All right?
What depth of recursion do you when we define?
Well, I mean, you know, this. So you see, here we go over the neighbors, right? And then we calculate this. I mean, it should go through all the in recursive iterations. Should go, of course, through all the nodes eventually, right? If you look at this definition, we go through all the nodes. If we go through all ij's, calculate through all ij's, it eventually goes through all ij's, all k's, m's in the graph. So I mean, it will capture patterns among all the nodes. And the depth of recursion is the number of iterations you need for this to converge, right? And I mean, I cannot tell. But if you go and look at the paper, they might have some, estimates of how many iterations you need to do to get conversion. Okay? All right. Now let's switch the topic a little bit, but we're still talking about this network connectivity patterns. We're going to talk about this notion of assortative and disassortative mixing, which is actually quite useful. The idea is the following. If we look at the networks, at the social net, for example, social networks or any other networks, and the nodes have some attributes associated with them, for example, age or gender, if we talk about social network, or income, if we talk about, I don't know, professional networks, then it is quite often that within social networks, people with the similar attributes connect with each other more often than with different attributes. Which means, think about age, people often have most of their friends, similar age, right? Or, if you think about income, and also think about your friends, quite often, your friends, your acquaintances will have similar income to yours simply because that's how, they might have similar interests, they went to the same college, etc., etc. So there are more often links in between nodes with similar properties than in between nodes with dissimilar properties. Right? So, when that happens, it's called assortative mixing. Or, for example, again, like political beliefs, right? There are more usually nodes, if you're, well, all right, no comment. Like if you're Republican, you're most likely your friends will be Republicans. If you're Democrat, most likely your friends will be Democrats, right? So that means, and there will be fewer links. There will be a lot of links in between nodes with similar attributes, and there will be fewer links in between nodes with dissimilar attributes. All right? And so that's a situation called assortative mixing. Now, you can have the opposite situation, which is called disassortative mixing. It is when the nodes, it's more often nodes with different attributes that are connected. So if you think about, again, social network, but like dating network, and you have your attribute is gender, you'll have probably more connection in between people with different gender, right? So different gender that date each other than the same gender. Food web, okay, well, you can think about predators and preys. Predators not connecting to predators. Predators connected to preys because that's what they are, right? And you can think about a lot of other types of disassortative mixing. Typically in social networks, aside from like, say, dating network, if you think about gender, we see assortative mixing. And of course, you want to be able to somehow quantify this, right? You want to be able to quantify this property. Well, how would you do this? Very similar to what we have done before, and actually we're going to go there in a second. This is an example of authoritative mixing, right? This is an old picture. Well, yeah, pretty old by now, 2011. So picture of tweets and their Twitter and their color-coded, and tweets and retweets, and they're color-coded by political affiliation, like more of like left and right wings. And if you notice, of course, it's people with one particular preferences, and the people with other particular preferences, they don't tend to retweet each other. Now, assortative mixing also have the name homophily, right? It also goes by the name homophily. So similar connects to similar, and that's called assortative mixing, right? And similarity here is determined by, in this particular case, by the label or by the attribute that associated with a node. In this case, it is political preference. Now, the question is if we can measure it, right? Because we always want to, just have some numbers and see if, for example, in one network, this property is much stronger than in another network. And one way to do it is through so-called modularity metric. And I wanted to pay attention to this metric because we're going to use it a lot for clustering and other things. And this modularity metric was introduced by Newman, probably in, 2010, maybe 2005, don't remember. Anyway, so the idea is the following. What we want to do is, when we measure things, we want to compare them. So we want to see if the number of connections between between the nodes with the similar properties is greater than we would expect in a random graph or in a random connections. Make sense? Imagine that you have. So what I want to do is the following. I always, we always try to have like relative metrics, and the idea here is the following. In order to understand if what you have, if the connection, if you have a connectivity pattern, the one you have, is significant or not, what you want to do is you want to compare it against something. So have some baseline. And so baseline would be the following. Imagine you have a graph with the same mix of attributes, right? With, let's say, male, females, I don't know, left wing, right wing, Democrats, Republicans, there's nodes. And then you take your edges and you randomly throw them on this graph. You probably expect, like, let's say, if you have the same number of nodes of both colors, you expect that probably the number of connections between nodes of different colors and between nodes of the same colors will be what? The same, right? Because remember, if you do it randomly, it's just you pick up two nodes and you just connect it or not. So that's your baseline. And then you take your graph and you actually calculate if there is any bias, if there is any sort of, if within your graph you have more connection between nodes of the same color or the same preference than, between than within, right? And so that's what this says, literally. This matrix measures number of edges between vertices with the same attributes. And this is expected number of edges if you had a random graph. And the random graph here, the meaning is that you randomly connect things. Okay? And this is then you calculate this coefficient. Now, why is it this way? Well, let's just go over it once. Ci and Cj would be the attribute of the node, class that node belongs to. Say male, female. That can be male, female, I don't know, Republican, Democrats, etc. So delta is a Kronecker symbol. You guys familiar with that notation? No? Yes?
Yes.
So what is it?
Inside 0, 1.
It is 0, 1. If those arguments are identical, it is 1, and if they are different, it is 0. So what this says, this Kronecker symbol says if your labels are identical, right? If the two nodes, let's say both Democrats, this is 1. And if this label is Democrat, this is Republican, this is 0, right? If those two Republicans, this is also 1. And this goes under the sum. And so which means the sum only takes into account the nodes that are of the same class, right? When the both nodes are the same class. And this is your connection between them. And then, again, it adds to the value only if the nodes within the same class are connected. If they're not connected, if nodes I and j are not connected, aij is 0. aij is not 0 only if they're connected directly. And if they're the same class, then it adds to this sum, right? And so literally it just counts how many connections you have within the same class. And this term, it actually comes, and we talked about it before, it comes from the random network, so it actually tells you the probability or expected number of connections if the graph was random, if the connections between two nodes happened at random, and that probability is proportional to the node degree of I and node degree of j. We talked about this a few lectures back. And so that's pretty much what it is. It says, it kind of calculates the difference in between the actual number of connections versus expected number of connections in a random graph. And that's called modularity. Okay? And then you can actually also talk about, from this you can derive various coefficients. One of them is called Authoritativity coefficient, which is the modularity coefficient normalized in a certain way. Some people use it that way. Some people just use it directly modularity. I think most of the people now just use this as a metric for attributes, for associative mixing. Now, that was metric that had to do if you had labels that are, the attributes that are labels that, like sex, like, I don't know, like political preferences, which is categorical, right? So it's a category. Now, if your attribute is a number, let's say age or income, then you can actually do very, very similar story. But you can explain it the same way as I explained before, or you can think about it as literally correlation. So what you do is you calculate correlation in between the values of two nodes, but you do it only if they're connected. So, I mean, usual correlation, right? Pearson correlation, typical correlation, but you do it, you only take into account the correlation between nodes when they're connected. Now, how do you calculate correlation? You take one value and multiply it by another value, right? That's your correlation computations. So that's what's done here. You take one value, multiply by another value, but you add it to the sum only if those two nodes are connected in your graph. And you also here it's subtracted k, kj, but in fact, surprisingly or not surprisingly, this explanation, in fact, it just corresponds to typical computations of covariance and variance. So if you take this formula for covariance, xi, xj, right? This is how you calculate covariance between two vectors, right? And so xi minus average, xj minus average, but again, the difference to typical data mining or data analysis, the only difference is here I multiply it by the connectivity. And so it is taken into account only if the nodes are connected. All right? So, bottom line, if you have categorical attributes, labels on the nodes, and you want to calculate, to see if the connections are sort of balanced, right? Or if there is any bias in terms of connecting one type of nodes connecting more with the same type of nodes than with other nodes, you calculate this modularity. If you have numerical attributes, scalar attributes, numerical attributes, numbers, you just calculate correlations, but those correlations are adjusted through the connectivity pattern. And then there is this notion of assortativity coefficient, which is, again, very similar to correlation coefficient, which is covariance divided by variance. And that's called assortativity coefficient. Within network X, I think there are functions that just calculate modularity and calculate assortativity coefficient for you. So you don't really need to calculate this yourselves, but you need to understand what they mean. Now, finally, there is actually one important use case, important situation for this type of scalar mixing. And that would be the following. We can actually think about properties of the node. We can think about the node degree as a property of the node, right? So we talked about property of the node being, let's say, salary or age, but you can also say the property of the node is how many friends it has, right? That's, it's a numerical property. And so then the question becomes, but then we can start thinking about the story. If we have a graph and we look at different nodes, do we see that the nodes with a high degree, with a lot of friends, connecting to the nodes with a lot of friends, and nodes with a fewer friends connects to the nodes with a fewer friends? Do we have this situation? Or do we have a situation when somebody with a lot of friends connects with somebody with a fewer friends? So what do you think happens in a real social network? Yeah, you wish. Nah. It's quite strongly the story of high connected nodes connecting to high connected and low connected to low connected. Nobody likes losers, so nobody wants to be friends with somebody. So it's the same as income, right? It's people within their strata that are friends and they're connected. And so that's very, very strong property, and you observe this. Yeah.
When we calculate the correlation between different centrality measures,
Yep.
high degree centrality is correlated with other
High degree centrality. Yeah.
with other centrality measures that are based on the centrality of neighbors and all this stuff. So if they're correlated, then high degree nodes
Will connect to high degree nodes. Yep, you're right. And that's what you observe in typical social network. Now, here I just want to, there are ways to simplify things when you put in node degrees. So the only thing I do here is I take this formula, and instead of xi and xj, I put node degrees in there, right? And that is called mixing by node degree, or sometimes people call it assortative mixing by node degree. So you just calculate it with a node degree. And it's actually very visual, the different type of mixing. I put in what's what, but I just wanted to ask you guys. Obviously, look at this one versus look at this one. This one is assortative. This one is disassortative network. Disassortative network, there are nodes of high degree connected to the nodes of low degree, right? This is tree-like structure. In assortative networks, it's a node of low degree connecting to nodes of low degree, and then there is as well, we can barely see it, but nodes of high degree connecting to nodes of high degree. All right? So you can actually even visually distinguish it. But you can calculate that property, the node degree, mixing by node degree it's called. You can also go a little bit deeper, and instead of just one number, if you want to know a little bit more about your graph, you can calculate just a correlation matrix in between node degrees, right? And you can barely see it here, but let me explain. What you see here on the axis, this is a node degree of one node, and this is a node degree of another node, right? So these are different node degrees. And what is calculated, every point here, every cell, is a probability that a node of degree, let's say 5, is connected with a node of degree 5. And you calculate it by just, counting literally how many nodes of this degree are connected within your graph. And then this is, for example, probability of the node degree 10 connected to node degree 10, and probability of the node degree 20 connected to node degree 20. Now, if everything is kind of neutrally, if everything is mixed up and things are like, different nodes connected to different nodes, like high to high degree, high to low degree, then the probability, this correlation matrix will be very, very symmetric. So the probability of nodes with different degree connected with nodes. Let's say take node degree 5, probability is connected to node degree 5, 10, or 15. It's pretty much the same. This situation tells you that there is a probability of 5 connects to 5, 15 connects to 15, but probability that 15 or 20 connects to 5 is very low. But the probability that 20 connects to 20 is still pretty high, right? So this is authoritative mixing. This is a signature of authoritative mixing. So you're again, 5 connects with 5, 10 connects with 10, 15 connects with 15, 5 does not connect with 20. This one is opposite situation, where the nodes of high degree connects more with high probability with the nodes of low degree than other way around. And that's disauthoritative mixing. And here there is even cartoons, right? High degree nodes connect to high, low degree connects to low, and this one is when it is opposite. And this picture you get when you get both of the situations, right? Make sense? So this is a correlation matrix of connectivity in between nodes of different degrees. And that's also sort of a good way to analyze your network in terms of if you want to know if it is authoritative, disauthoritative, that picture, that graph will tell you. All right. So to sum up, there are a bunch of papers. I actually put here only most recent, though if you notice, there is this 85, 89 kind of stories, structural, regular, relational equivalence, regular equivalence, that's what we started this lecture with, and then there is a story on vertex similarity, structural similarity, and then there is a story on authoritative mixing with Mark Newman. So if you're interested, read this. Practically speaking, you just need to understand, what structural similarity is, how to measure it, how to compute it, and the authoritative, disauthoritative mixing, that is a very, very popular measure, and so that one you need to really know how to use. Okay? Any questions? No questions. All right, 10 minutes break, and then we'll go for the next part. So we're going to continue talking about network structure, and this will be the first lecture that kind of takes us into the topic of communities, community detection, network communities. Before we do that, we're going to talk about a few very, very practical things, very practical applications, very practical definitions. And we're going to start with a story of core and periphery structure of the network. Now, before I go there, if we look at this network, there is a lot of structure in here, literally, right? So first of all, you got few nodes here that are isolated, right? They're not connected to the graph, disconnected part, right? Disconnected component. Then you got something going on here. There is there is a node, and there is like a lot of connection. Then there is sort of chain things happening here, and then there is a lot of nodes right there in the group. And so, if I ask you to find here within this graph some sort of the core of the graph, like the central part of the graph, without yet defining what it is, where would that be? Like, if you think about like geometrical part of the graph that you think might be, the most central in some sense, where would that be? What would that be? Clear, not these guys, right? Yeah. Now, this, it's well connected, but it's kind of far away from everything else, right? There is no direct connection here or there, so you kind of go with it. So probably not that. Here could be, maybe this, I don't know, right? And it depends on the definition, of course, what we call centrality. But like purely intuitively, right? If you look at this graph, and I'll ask you, like, look, where do you think is like the most important, like sort of central part of the graph? Where is it? Probably somewhere here, very dense and well connected. So there is a very formal definition that allows us to answer that question. And if you look at the graphs, quite often they have this so-called core periphery structure. Core, there is usually a region of the graph, of the network, where we have a very dense connectivity patterns. So there's a bunch of nodes, and they're connected among themselves. And then quite often you have this sort of hanging out like, long pathways, and the guys call them whiskers in their paper. So groups of nodes that's, connected, but then there is usually sort of a long path to the core. If I bring back to, you realize here that this guy, again, they're kind of connected, but then there is a sort of long path to the major part of the graph. So the question would be, can we actually take a graph and detect this core? So split the graph into this core and periphery. Now, it's clear that we cannot define very well, uniquely what core is. We can think about the sort of layers, right? You can think about the very center part, very dense part of the graph, and then there is like layers of nodes surrounding it, and eventually you get to like this whiskers or periphery. But there are a couple things that can be, defined precisely, and there is actually a very, very nice definition notation of the core. We're going to talk about it, and it is actually extremely, extremely practical. And the reason is the following. Quite often, later on especially, when you start doing like, community detection, you would be interested in things happening here. You would have less interest in things on the periphery of the graph. They will be trivial, but they're still part of the graph. And so detecting those pieces and removing them can be extremely helpful, because they're not helping you with solving your problem, for example, finding communities. But at the same time, they increase the size of the network, the size of the graph dramatically. And so quite often you want to do this type of preprocessing and pull out the very center, the core of the graph. And I'm going to define now what core is. Can you see anything? What, on that? No? Barely? Yeah. All right. So let's do the formal definition. I'll walk through this slowly. And it's actually, again, this topic is extremely practical. So this core structure of the network, you'll be, if you do network science, you use it constantly. Okay. So a K-core, the definition. A K-core is the largest subgraph such that each vertex is connected to at least K other within that subset. So, for example, 2 core, it is the largest subgraph where each vertex is connected to at least 2 other vertices within that subgraph. At least 2 other vertices, which means it can be connected to 2 and more, which means that 2 core can contain nodes with degrees greater than 2. So this is not a node degree, right? That's very important. Now let's look what this is. Let's look at following the definition, and then we'll talk about practical algorithm of finding those cores. So the core of the 3 core, or core of degree 3, it means it's the largest subgraph within the graph where each vertex is connected to at least 3 other in subset. So if we look at this graph, okay, this node is connected to 3, this connected to 3, this connected to 3. If I pick up this node, it's only connected to 2. So even if I add this to subset, it's not going to work, right? So the 3 core is this structure. Now, if I go and look at the 2 core structure, then it's going to be this structure that consists of red nodes and yellow nodes. Why? Well, because a 2 core is the largest subgraph such that each vertex is connected to at least 2 others within subset. Within subset, right? So this connected to 2 within subset. If that is my subset, this you don't count because it's outside of subset. This connected to 2. This connected to 2, this connected to 3, but it is, at least 2. This connected to 1, 2, 3, 4, 5, 6, but it is at least 2, right? So when you define cores, you can also define what's called K-shells, and K-shell is the nodes that belong to the bigger core and do not belong to the inner core. So for example, this is a core 3, this is a core 2, and the shell is those yellow nodes. Core 2 and core 1, and the K-shell, one shell, is those blue nodes. So cores, in this sense, is you can think about it as like, peeling the onion, right? You kind of layer after layer after layer, and the core is what's starting from this layer going down, right? Now, it's actually easier, and I mean, it seems like very easy definition, but you need to think about it, so it will kind of sink into your brain. What this means, it's much easier to actually, in practice, to to have this practical approach to K-core decomposition, or understand how it works. Let's look at this graph, right? And again, remember this analogy with an onion. I want to decompose it into the layers of different connectivity. Now, of course, it's this picture is kind of artificial picture, just for the ease of understanding. But this is the approach I would take. Look, what I'm going to do is I'm going to recursively delete all vertices degree less than k. Then the remaining graph is k-core. So, first of all, this big thing, the whole thing is a core equal to 1, because every node in this picture is connected to at least other node within the subset of this whole thing, right? Now I want to find core equal to 2, or 2 core. To do this, I need to delete all vertices of degree less than 2. Yeah, easy, right? So I delete this vertex, it's degree 1, right? I delete this vertex, it's degree 1. Delete this, 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 this. But then what happens? There are several vertices that were degree 2. This one was degree 2, and this one was degree 3. But after I deleted those vertices that are degree 1, the degree of this guy dropped, and the degree of this guy dropped and became 1. And so I also want to delete it. So the key word in this definition, in this approach, is recursively delete all vertices degree less than k. All right? Makes sense, the process. So you take a graph. You want, for example, to find the 2 core in the graph, or core of degree 2. What do? You take and remove all the nodes of degree 1. Easy. But then what happens? Some of the nodes will drop their degrees from high degrees to 1. Like here. There was a node of degree 3. After I removed these 2 guys, degree became equal to 1. Right? This guy had degree 2. I removed this one. Now it has degree 1. So I need to go again through all the nodes and again remove those that are now degree 1. And just keep doing it until no more nodes of degree 1 left. And then you get the score number 2, the green, this thing, which is green and what is it, purple. Right? Makes sense, the process. The next step, if I want to do core 3, what I'm going to do is I'm going to remove all the nodes of degree less than 3. Then some of the nodes will drop their degree, and I'll remove them. Okay? And this iterative process will actually generate for us those subsets. And then, if I calculate this core 2 and then I calculate core 3, well, the difference, the nodes that are part of core 2 but not part of core 3 is called, K-shell. And what's color-coded here is shells. K equal to 1 shell, K equal to 2 shell, K equal to 3 shell. Now, K equal to 3, it's a shell and also core itself, right? Because there is no way to go deeper. Notice that the higher the core, of course, the denser is a pattern there. But it's not necessarily clique. So it is not necessarily that you have everything is connected, but it is the densest part of the graph. And core 1 is this sort of sparsest connection. And core 1 allows you to get rid of long chains that are attached to the graph. Because, again, if you have a long chain, for example, and you say, let's remove nodes of degree 1, well, this will not cut out the chain, because every node in the chain has degree 2, except for the last one, right? You cut it out, well, you still have your chain. And so you need to recursively do it until you reach the point where the node degree, after you remove its neighbor, is not 1 anymore. All right, I pause here for a second. Does this make sense, what we're doing? So notice, it is, again, this is very, very, very practical technique, because if you notice what I just described is an algorithm. And what's the complexity of this algorithm? It's almost linear, right? It's just a little bit more than linear because you need to iterate several times. But it is linear, right? And so that means it works on like graph of any size. And so that's why it makes it very, very practical. And it also allows us to get rid of like a lot of sort of hanging nodes outside of the graph. And very important, when you do this K-core thing, again, it's not about it's not only about node degree, it's about how it is connected to other nodes, right? Because when you do this sort of peeling off nodes, some of them drop their node degree, and so then you have to remove them too. Okay? So, I mean, you can probably run into this observation, importance of the story in the following way. Imagine that you have you take your graph and you calculate, you draw the histogram of the node degrees, right? And you have some number of nodes of degree 1, number of nodes of degree 2, number of nodes of degree 3, etc., right? Then you do the following exercise. You say, oh, heck, I don't want nodes of degree 1. You remove them. Just remove node degrees 1. Nodes with degree 1, right? Then you then you calculate the histogram again. And quite often, to your big surprise, there'll be new nodes of degree 1, right? No, because you removed only nodes of degree 1, so some other nodes drop their degree to become degree 1. So you draw the histogram, you again got them. You're like, what the hell? But then you do it again, and eventually you're out of those degrees of node degrees 1, and your histogram has node degrees 2, 3, 4, 5. Okay, when you've done this, you calculated two core of the graph. Right? Okay. We should actually have done this exercise before I was explaining what core is, just to make you do it at, in a seminar, to actually remove degree 1 and see what happens. All right. So here is an example. That's, again, the karate graph. I like playing with it. It's small. So you can actually calculate the cores here, core structure. So it's color-coded like opposite way, but this is a core 1, core degree 1. This guy's is yellow guy's is core degree 2, green, and here's core degree 3, and this is the largest core 4. And it actually does what you sort of intuitively expect, right? It actually pulls out in core, in the deepest core, largest core, it pulls out the densest, the most densest connected part of the graph, right? Okay. This is an example of a large graph also processed using this K-core decomposition, and you notice this is a very, very dense graph, and there are a lot of sort of tree-like structures that are hanging out there. And quite often when you look for, again, when we start looking for communities, those things, these are not communities, right? These are not nodes connected to each other tightly. This is just kind of this chains hanging out. And what you want to do is, cut them out. I mean, again, with this graph, it looks like, oh, fine, I'll just go through by hand and remove them. But that's not going to work by hand because the graph is pretty large. But K-core does it for you. And then you can, this is core, second core, and that's its third core. So So that's how it works. Okay, any questions about cores? Make sense? Sort of makes sense?
Can we return to 2 slides? Yeah.
This one?
No, the next one, yes.
Yeah.
And again, the core is, the yellow are
The shell. So color-coded are the shells.
the shells, not the core.
No, the core is, okay, so the core is, again, like shell is, again, if you think about this onion thing, like a shell is a layer of an onion, and core, what's remain, from this layer down.
It's like edges.
Yeah, so this core, so shell 1 is this red, core 1 is everything, because they all have connection at least to one node. Then you cut it out, core 2 is everything, and shell 2 are those yellow guys because they have no degrees 2. And then you cut them out. What's left is this, which is core 3, right? It consists of 2 shells, 3 and 4. And then you go deeper, and this is core 4. Okay? And here I also try to color code it. This is a outer shell, and then I remove it. What's left is only this green thing, right? And then you just keep digging down. You can barely see it, but eventually there is actually a clique in there. And the core decomposition allows you to disassemble it into this. Very, very nice. And again, I mean, I think the reason people love it and use it a lot, first of all, is when you start understanding it, it's quite intuitive, and second, it's linear in terms of complexity. And so that means like any graph of any size, you can deal with it. Later on, we'll look and see that when we do community detection, there's no linear algorithms. They're all n something, right? At best, n log n, most likely it can be like even up to, n square root of n, n 3/2, or even n squared, which is in a large graph is impossible to do, just because it's too much. And so this allows you to take big graph and remove the things you're not interested in. Okay, all right. So one other thing which we want to talk about before we go into communities is the notion of a clique. Do you see cliques here? Yeah. This one? More? There's another one. More. Yeah, there's this one. So actually we're good with eyes, detecting cliques. But it's because, again, the graph is very small. The question is, as always, well, can we actually detect them automatically? And also, we intuitively, see this thing as a clique. Now, the formal definition is actually slightly different. This is the maximal cliques that we see. I'll explain in a second. Just to be precise, right? So the clique is a complete set of vertices where each pair of vertices is connected, right? That's the definition. Now, let me find it in here. Well, actually, let's go to the next one. I'll go to the next slide. Actually, no. If I take this 3 nodes, is it a clique? Yeah, it is, because it's a set of vertices where each pair of vertices is connected. So it is a clique. In fact, if I take 2 nodes and they're connected, it is a clique based on the definition. So, we're not looking into this. We're looking at these guys, right? And so we're looking at what's called maximum cliques. So those that actually, the largest here. We'll see in a second definitions. So there are slight differences here. There's a maximal clique. It's a clique that cannot be extended by including one more vertex. And the maximum clique is the largest out of the cliques. So this one, right, this is a maximal clique because if I take the 3rd node and extend it, it's not a clique anymore, right? Because this node is not connected to this. So in here, this is a maximal. If I go back for a second, this is a maximal because if I take any other node and say, oh, it also belongs to the clique, what I get is not a clique anymore, because this is not connected to this, and not connected to this, and not connected to that, right? And so maximal is the one that you cannot extend anymore, right? And we by our eyes, identified those nicely here. But, you know, strictly speaking, there are many more cliques in here, right? Every edge is a clique, and every triangle is a clique. Now, this is just sort of the maximal because we cannot extend it. And out of these three, this is the largest. It has 1, 2, 3, 4, 5, 6 nodes. And so that's a maximum clique in the graph. Now, when you talk about cliques, that's like very much, you know, about cliques and graphs. That's part of, you know, discrete math, sort of classical science. And honestly, the challenge with those cliques, and here again I show you, this is a maximum. This is not maximal clique. It's a triangle, it's a clique, but not maximal, because if you add one node, it will be a bigger clique. This one is a maximal because you cannot extend it. If you take this node, this is the only node you can add. If you add it, it's not a clique anymore. And it is maximum because it's the largest possible within this graph. Now, these are very nice, very precise definitions. There are two troubles with this, as always. One trouble is, we'll go there. One trouble is computational complexity. It's actually pretty hard to detect those cliques. You actually need to go and do pattern matching through the entire graph. The second problem, in the real graphs, again, there's not that many cliques, like perfect cliques, like interesting cliques. Interesting maximum cliques. I mean, of course, they're triangles, right? But something interesting is not there. And in fact, that's quite often the difference in between the algorithms and stuff people look into, like when they talk about graph theory, you know, discrete math, sort of classical thing, and what network theory does. Here, people like very much, I mean, this comes from math, right? And theoretical computer science, and people love very much very precise algorithms, precise definitions. But unfortunately, in the real world, that often doesn't work because you don't have exactly like perfect structures. And that's why here we kind of try to, instead of talking about cliques, we're going to talk about communities, right? Though in fact, of course, clique is a community. It's just the fact that, you know, there's not that many cliques out there. And it's actually hard to find them. All right, so, but if the graph is small, you know, you can do it. And just again, to talk about this, this is a quadratic graph. And, you know, there are 11 cliques of size 2. There are 21 cliques of size 3, maximal cliques, right? There are 2 maximal cliques of size 4, and there are 2 maximal cliques of size 5. And maximum clique, so maximal, here they are. There are, you know, of size 2, 3, 4, 5. And the maximum, of course, is the largest out of them. The maximum clique here of size 5, and there are 2 of those, and here I show them on the graph, this one and this one. It's not so obvious in this graph, you know, that you have them, but you do. So it works on small graphs, but if you look at the complexity, you realize that on larger graphs, it's a problem, right? Large graphs, large cliques, it's a problem. Size of the clique, size of the graph. Right? Now, there are some algorithms today that can do it faster, and they also look for approximate things, but that's where we're getting into this community detection story. But overall, yeah, that's kind of not very practical, the clique thing. But it's beautiful. Okay, now communities. We're going to talk about communities next. On the next lecture, we'll actually dedicate 2 lectures to the algorithm for community detection. But right now, I just want to define it and, you know, go over one of this sort of algorithms. So as I said before, you know, clique is great. The problem with cliques, well, there's not that many in the real world. But you do want to see groups of nodes that are tightly connected to each other. Now, we did the k-core decomposition, which found for us the core of the graph. But now I want to find just not necessarily the core, not necessarily the sort of center of the graph, but I want to find groups of nodes that are connected or tightly connected to each other and has less connection with the rest of the world. Now, it's not a clique because there are a lot of edges that are missing. Like there's no edge here, there is no edge here, there is no edge here. So that's not a clique. So it's not about clique detection. But it's about finding a group of nodes where you have more nodes among them than with the rest of the graph. Now, the trouble with this type of definition is, on one hand, it is because it's kind of relaxed definition, right? You can solve this problem, and you can find algorithms that do it with a good computational complexity. The trouble is, because it's not precise, there are various ways to do clustering, and there are various results that all kind of fair. There is no sort of unique definition. With a clique, you have a very precise definition, right? It's a group of nodes, each node connected to each other node. That's it, right? And if it's not a clique. Done. Here, we're saying that, well, it's a group of nodes where vertices within the group connected with more edges than between the groups. So it is a very, very relaxed definition. And you will see that, in fact, you will see later that many algorithms within the same graph find very, very different network structure. I'm sorry, very, very, very different community structure. It is somewhat similar to clustering problem, right, from data mining. So you remember, when you do clustering, if you take different algorithms, you might actually get different results. Plus, let's say you use your k-means. How do you find k? What do? You say, okay, k equal 5. Yeah, look for 5. You check different. Yeah, you check different Ks, and then you say, okay, let's compare, let's say, the density inside the cluster with the density outside, or the distance between, the average distance between the cluster node, the average distance between points within the cluster, right, and the distance between the clusters, things like that, which is also very imprecise, and that's why different clustering algorithm will give you different clustering of your data points. So the same thing is here. Different community detection algorithm can easily give you very different results, unless you have a very simple graph where things are obvious. Plus, as again, the same way as with clustering, you don't know how many communities you need to look for. And some of the algorithm asks you, like, for how many communities should I look for? For 2, for 5, for 10, right? And then you do it, and then you say, okay, well, it looks like there is a metric that tells me that my community detection or my community partitioning of the graph into communities is better than yours, right? But based on the definition, there is no precise condition that has to be satisfied, except for density has to be the number of nodes more than in between, right? And in fact, if you look probably in Wikipedia, you might even find a slightly different definition of what community is. Now, we're going to consider non-overlapping communities, which means when we say the node belongs to a community, it belongs only to one community. And in that case, this community detection also becomes what's called graph partitioning problem. So graph partitioning problem means the following. You remove edges of the graph such a way that you disconnect it into subgraphs. For example, if I somehow can detect and determine that I need, I can cut out these 2 edges, I can cut out this edge, and I can cut out these 2 edges, somehow magically I know what I want to cut, right? Then I get 3 communities. Like, they'll be completely separated. So in this sense, community detection, if you have non-overlapping communities, you can think about it either as looking at the nodes and the connectivity pattern inside and saying that the connectivity pattern here is greater, the density of the edges here are greater than the density overall or the density in between. Or you can think about them as sort of edge removing process. You remove edges, and that splits your graph into pieces. Okay? But you can do it only if you have non-overlapping communities. Next time we'll also talk a little bit about overlapping communities. So, and I mean, eventually, as a result, what do you get as output from a community detection algorithm? You get an assignment of every node to some community. So it will just say, if this is node number 1, belongs to community 1. Node number 2 belongs to community 1. Node number 3 belongs to community 1. And let's say node number 51 belongs to community 2, right? So that's going to be your output from graph partitioning or community detection algorithm. Now, there was like a lot of discussion, what makes a community. And if you go and look at the sort of Bible of social networks, like Westerman and Faust's book, sociologists, right? They kind of started this whole discussion about social networks. They talk about community, a cohesive subgroup. They list those properties, like mutuality of ties. So almost everyone in the group has ties or edges to one another. But they say almost everyone, not everyone, but almost everyone. If everyone would have ties, then it would be a clique, but it is almost. So, again, you have a lot of connections, but not necessarily each to each. It's compact, which means, it's very easy to reach from one node to another within this group. So, not necessarily maybe one step. If it is one step, it's direct connection, but maybe 2 steps away, right? So it's very compact. If you think about density of edges, it's the density of edges within the group is higher than the density of the edges in between groups, and often than the density of the edges in the graph. And that's pretty much the same thing here. Is a high frequency of ties among the group members compared to non-members. So these are all kind of qualitative properties, right? And for us to build algorithms, we need to convert those qualitative properties into something that's measurable, something quantitative, right? Or quantitative. So there are some of those things that we can do. One is we're going to look at the community, right? And we can actually just calculate density, like literally. Take the group of nodes and calculate the density. The density is computed by number of edges divided by the maximum possible number of edges within that group of node, right? So for the clique, what density would be for the clique? 1, right? And so, the higher the density, sort of the better is your community. And you can, for example, compute internal density. So for the edge, based on the edges between nodes that are inside, and external density edges. And then you say, okay, well, if internal greater than, average density and external is less, then, that's your cluster. I mean, the great idea, right? Where is the catch? Why can't you do it that way? Let's for a second forget about directed graphs. We'll get them back later. Undirected graphs. Well, the catch here is what I just described is a metric, not an algorithm. And so even if we decide to do it that way, we still need somehow to find out those nodes or groups of nodes for which we calculate the density. Now, this is a factorially very, very large problem if you think about it, right? What I'm saying is you have this n nodes, and you need to find groups of nodes. Let's just do it brute forcefully, right? You go through all the pairs, for example, at first. Let's say I want to find, I take this node. It can be paired with, any other node it's connected to, right? Then I take those 2 guys. I go for the 3rd node, right, and the 4th node. So there is factorially large number of possible combinations, even if you fix the size of the graph. I'm sorry, the size of the community. It's also the same type of a problem as we have with clustering, right? If you try to put, arbitrary points together and just go through all the possible combinations, it's just too large. You cannot do it. So we can use this metric, but we need some algorithm. Yet there is another metric, which in fact is quite efficient, and people like to use it. And we actually saw this metric, the modularity story, right? Remember, we talked on a previous lecture about modularity based on the fact that you have two nodes, and when we talked about authoritative mixing, we just said, okay, well, this node is of Democrats, this is Republican, if they're connected, right? What we can do if we think about clustering or community detection, what we could do is we say, okay, this node belongs to community 1, this community 2, this community 3. And then, based on the same metric, the same modularity score, calculate how many edges are between the nodes that belong to the same community, to the same class, and how many edges are between the nodes that belong to different communities. So it is exactly the same story as what we had for authoritative mixing, except for now we don't have, for now the property is meaning the belonging to the same community. Does this make sense? And so it's exactly the same metric. That's modularity score. It's the same sort of, it's adjacency matrix, and that's what comes from random graph. You can also, in fact, and this is this delta Kronecker symbol we discussed. Now it's going to be 1 if the nodes belong to the same community, and 0 if they belong to different communities. You can actually take this formula and rewrite it, introducing the following notation. If you actually, instead of summing over pair of all edges, of all, this is double sum over all nodes. You can convert the sum into summing over edges, and then what this really says is the following. It's a number of internal edges of the community and divided by the total number of edges in the graph. So it's just a fraction of edges that are within the community divided by the total number of edges in the graph. And then this is the sum over all communities, right? That's very easy. And this one is, again, it is, this is sum of node degrees within the community, but this term comes from expected value if the graph was random. And so, again, we want to detect communities by comparing them to baseline. And the baseline is a random graph, and we assume that random graph doesn't have any communities because the random graph has connections, right? Random connections. So there is no community structure. And so what we want to do is we take our structure and compare it, contrast it against the random graph structure. And so this tells us about our graph, and this tells us about what would be in the random graph if it had the same number of nodes and the same number of edges, but they were distributed randomly. And it is quiet. All right, well, again, the best thing to do is to actually, you'll have to try these formulas and see how they actually work. Now, just to give you an example, this M, modularity score, well, Q or M, it's the same. It's just, again, different books use different letters, but this is the modularity score. This is this modularity score. If your graph belongs to the same community, right? All the nodes are part of the same community. This modularity score will be 0. Okay? Now, if you look at this graph, and like different color coding, and the color coding will mean the community, which one do you think is the best partitioning into communities here? Yeah, this guy, right? Why? Easy, yeah. So why?
Because nodes from the same community are very close to each other.
No, but I mean, why do you think that this is a better community than, for example, this partitioning into 2 communities? Or this partitioning into 4? Well, because, yeah, if you look at this, you just can, for example, cut one edge and it's split into 2 groups easily, right? Here, to split this into 2 groups, you need to cut 1 to 3 edges. Or you can think about, like, on average, if you look at these guys, the number of edges connecting them internally, and these guys internally versus them interconnected, here it's the density is much higher, right, than this. While here it's kind of worse, and this is just a mess. And again, with the simple graphs, we're very good with our eyes detecting communities. It's just the question of doing it in large graphs and consistently. So the point is, this metric, if everything belongs to the same community, this metric is 0. It's very obvious from the graph, from the formula. If there is a very bad distribution, this metric can actually become negative. This partition, it's also suboptimal. This metric grows because this is better than this, but still not very good. And this one gives us the largest value for this modularity. Okay? So on this very simple example, looks like this modularity metric works actually pretty well. And in fact, it does work pretty well. It has its own problems with large graphs, but there are a lot of algorithms that actually either directly maximizes this metric, right? So trying to calculate it on every step and maximizes it to give the best partitioning, because again, the maximum value is the best partitioning. Or other algorithms that optimizes something else, but checks on this metric in terms of, verify the quality of what they have done. Okay? So we'll talk about one very simple heuristic approach, and again, surprisingly, it's the same guy. It's again Newman who actually wrote the paper on this partitioning. He did a lot of work on it. So we're gonna do a very, very simple intuitive algorithm for graph partitioning or community detection. Now, let's say we do want to go right now and we want to split the graph by cutting out edges, right? So like you proposed back on the previous slide. How would you identify the edges that we need to remove? I mean, you can go through all the edges, no problem. But for every edge, you need to decide, you keep it or you remove it. So how do you identify the edges you want to remove? Number of, but it's an edge, right? So what do you mean number of neighbors for an edge?
So we see those edges. So we try to just compute the number of shortest path from each of the nodes, and if it has the most value, it means that a lot of shortest paths are going through different communities.
Right. So one of the ideas, and if you think about it, it's quite intuitive. Remember, we talked about the betweenness centrality, right? Which is the number of shortest paths that going through a node. Remember, right? No, it was an hour ago. Now, nothing prevents us from introducing the same type of metric for edges, right? Because for betweenness centrality, we talked about number of shortest paths that go through a particular node. We can actually talk about number of shortest paths that go through the edge, right? I mean, not a big deal. But then you can think about, imagine St. Petersburg, right? And you look at the city structure, and you start calculating, using your Yandex taxi or whatever to calculate all the routes and shortest path, assuming Yandex, that's the shortest path. Where would be the densest traffic? On the bridges, right? Because that's the only way to get from one part of the city to another. So bridges will have the highest traffic, and the highest number of shortest path that goes through them. But then if you think about, again, like, Neva River, St. Petersburg, if you want to do this kind of community detection or clustering, probably if you cut the bridges, that will give you very natural community connections. And so the same thing is here. You want to detect communities, well, let's find those bridges, those edges that are bridges, and remove them. Okay? And finding bridges, we can actually do that by calculating all the shortest path and selecting the one that actually has the largest number and removing it, because that will be sort of the bridge. Now, there is one catch with this story, of course, as always. You can do this, but what the problem is? Now it's actually a technical problem.
Counting of shortest path is difficult
Yeah, it's actually computationally challenging to calculate large short. I mean, its computational complexity is pretty high to calculate shortest path, and then you need to do it over and over again, because let's say you cut out one of the bridges, right? Then the shortest path changes. All the shortest paths changes, so you have to recalculate them. And so as is, this algorithm does not scale. Now, people introduced a lot of improvement, and eventually they made it scale. We're going to talk about like basic version, just sort of brute force. It works well on small graphs. It has issues with scaling because the shortest path it's hard to compute. Now, the easiest way to avoid this problem is actually, instead of computing exactly the number of shortest path, you do sampling, right? You just calculate, you randomly select starting points and you just do it on a sample, right? And so that's one of the ways around this problem. But in general, yeah, so that's the idea. You compute edge betweenness, a number of shortest path going through a particular edge. Then you rank all the edges by that number. Then you pick up the one that is the largest, right? In terms of like the heaviest traffic would go through it. You cut it. Then you recompute again all the between the centrality for all the edges. You select the next one, and you keep doing it until your graph disconnects. And I mean, after you do like the first cut, you check for connected components, right? And if it's still connected, well, you do the second cut. It's still connected, do another cut. And then at some moment, of course, it's going to split apart, right? Make sense? Yeah, yeah. Let's actually get to this point. Obviously, if you just you keep cutting, then it will split apart. You will get partitioning into two groups, right? If you think that there are more clusters, there are more than two, right? If you just, by whatever reason, you believe that there are more communities than two, you just keep going. Because I mean, what really happens is usually with this algorithm, you cut out one community that is very well defined, but then you have the rest of the graph, right? And then you just keep cutting. So it's sort of divide and conquer, right? You do it once, then you do the same process on each of the subsets you got. But then the question would be like when to stop. And let's talk about it for a second. But before we go there, just again look at the algorithm. So this is edge betweenness, Newman-Girvan 2004. For every edge, compute edge betweenness, remove edge with the largest betweenness, recompute, keep going. So as a result, you can actually get the partitioning tree, right? You can have a first split, first cut, then you keep cutting, keep cutting, right? Until you get pretty small communities. So one way to stop is, by the size of the community, right? If your community is, I don't know, and that's your parameter, right? You say community less than 100 nodes, I'm not interested, then that, like, stop cutting. And then, your partition will be like sort of have some kind of tree, partitioning tree will have some certain structure, and you'll get your communities, but the parameter is the size of the community. You can also monitor modularity, and that's what we're going to do right now in a second. Let me show you this on this karate club graph. So if we start with this Zachary karate club, this is a split number 1, right? So it cuts out a bunch of edges. I don't show the edges that are being removed, but I just color code communities. Okay? So pretty much the way it worked, using that algorithm, it removed the edges that connects red and yellow, and that's how it split it. But on the graph, of course, edges remains, right? Make sense? Okay. But now I can keep going with this algorithm, and if I keep going, now it takes this big red thing and splits into two, right? Green and what's left and red. And you just keep going. You can just keep going, descending more and more and more. And as I said, one way to stop it is by saying, look, I don't want communities less than certain size. Another way is to actually, on every step here, check the modularity. Remember, the modularity was here. We learned that when we hit the right number of clusters, and when our hit the right number of communities, and the community structure matches, the graph, well, this thing is large, right? Here we have two communities, but they're badly done. It's slow. Here we try to do 1, 2, 3, 4, 5, whatever communities, and it's also very low. So, since we're not using modularity when we do optimization here, and the only thing we're using is betweenness, we can actually use modularity to check how well we do, right? How good is our result. And so I can keep cutting and monitor the modularity score. And so when we had one complete, when the graph was single community, this is the modularity score is 0. Then we split in 2, that's what you get. In 3, that's what we get. In 4, that's the value. 5, that's the value. So according to modularity score, 6 is the optimal number of communities in that graph. And then if you split into 7 communities, the modularity score drops into like 10 communities, even less, 20 communities, even less, et cetera, right? So, but even looking at that graph, it was obvious that you don't want to have like 20 communities there. Intuitively, I'm not sure if this versus this, right? If 3 communities here is better than 2, right? Just by looking at it. In fact, the background story here, I think I told about it at the very first lecture, that this is a karate club where there were 2 instructors, and the sociologists were observing that club and friendship relationship, and at some moment there was an argument between those instructors, and they split into 2 different clubs. And some students stayed with one instructor, and others went with another instructor. And so there is a sort of ground truth in this test, in this set, but it's known, and this is original friendship. And so the idea was that, like, look, if we see original friendship, we can predict where the sort of split line will go, who will go with one instructor, who will stay with another. But the thing is, in real life, what happened, they split in 2, right? And so kind of 2, that makes sense here in terms of, and that's partition line, yeah, looked good. But for whatever reason, the algorithm, right, the modularity thinks that this is better. And in fact, this is the highest modularity. That's what the just pure score metrics thinks is the best. So based on the modularity score, this is the optimal number of communities within this graph. Now, you can argue that, that does make sense. Or you can say, like, look, it's weird. I would like 2 communities better. But, well, here it's clear that this is kind of can be cut out. This is probably can be cut out. That sort of also makes sense. This group doesn't make too much sense, but this group also kind of makes sense that it's tightly connected. So you can have arguments for and against, and also notice that splitting in 2 and splitting in 6, there is not such a big difference in the modularity score. So, bottom line, because the community detection is not very precisely defined, right? You can use different metrics. People come up with the metrics. We do have some hand waving explaining why I like the metric I use, and then I monitor it. We can also take the density metric and monitor that metric, right, using this algorithm. So you can come up with any metric and tell you, this is my metric, this is my community detection. But the story, my community detection is better than yours, is a very difficult story because it is really about the metric you use to define the quality. So it is very similar to clustering story where, look, this clustering is better than the other is very hard sell, right? Sometimes it's very obvious, but if I give you 3 clusters and then you say, look, but I can see there are more clusters within this cluster. Yeah, it's hard to argue. And that's why people very often when they do clustering, they, instead of just giving you a cluster or several clusters, they would actually give you the tree, right? Like agglomerative clustering, and then you're happy with that many clusters, you work with them, but if you're not, you kind of go up the tree and cut out as many clusters as you need. And the same way here, when people do community detection, very often they actually do it, build this hierarchical community trees, and then depending on if you believe that there are two communities, you stay here on this level, and if you want more communities, you go down, and even more and more and more and more. But again, having said that, if you use modularity metric, the best partitioning is this, according to that metric. Now, if I take a different algorithm and use the same metric, I might get different partitioning, right, and different value of the metric. And that algorithm might not give you this exactly the same partitioning because those algorithms are heuristics, right, heuristica. We are just trying to locally, optimize something, but we don't have a very precise criteria of what we're optimizing. Makes sense? Sort of, kind of. Okay. So, which means there is no unique correct answer when you do when you do community detection. Having said that, of course, when you have the same algorithm and the same graph, you expect the same results, even if it's done by different people, right? It doesn't mean that you're just going to get random crap. So, and if we give you homework and there is a graph and we know how this algorithm works in this graph, right? But at the same time, an algorithm can do different partitioning, and based on some metric, it could be better. So, murky story. Any questions about this? So next lectures, 2 more lectures, we'll actually dedicate to to the algorithm for community detection. Some of them, there are quite a few of them, now, and some of them are very efficient. Some of them less efficient. Some of them give you, better quality, worse quality. They're optimizing different things. The usual rule of thumb is pretty much very similar to what you do in machine learning, right? So, when you have your design matrix and you have your result and you have your train and test set, what do? Well, you take a bunch of algorithms and you run, and then you see which one behaves better, right? So the same way here. You take your network, you run a bunch of algorithms, and we're going to talk about those algorithms next time, and you check by different metrics which one gives you better partitioning. The only difference is to supervised learning, well, there is no ground truth here. So, it's somewhat more like clustering versus, not like supervised learning. And, as I said, within this Zachary club, this is a partitioning tree, right? And so the algorithm itself believes that there is that many different communities here, but, you don't like it, you kind of stay up on partitioning into 2 graphs. Okay. That's it with the lecture. Now, I would strongly recommend you read, this is a pretty long read, right? It's 100 pages. But it's a good, and it's 2010, there has been some developments since then, but this is a very, very good review. So maybe not reading, in depth, but kind of going fast over it, that would be very good. Right, very good pre-read for the next lectures. And today's algorithm is here. Modularity and community structure networks. Also take a look, read it, because that's where Mark Newman introduced modularity, and that's where he introduced this partitioning algorithms, the one we discussed today. All right, and we're done. Any questions? I'm sorry, say again?
Do you know whether the teachers of character teachers are represented in the character?
I think they were. I think they were I would suspect, honestly, that should be 1 and then maybe the 34, 30 something, because looking at the sort of connectivity structure. But I'm also, this is also very suspicious because these 2 guys have very similar structure. So if you Google Zachary Karate Club, you will instantly get the original paper that, the funny story about this paper is nobody, maybe some people in sociology knew it, but it had very little citations. It's one of the computer scientists found this paper with the data, and then the citations for this for the Jaccard Karate Club, research paper skyrocketed because all of a sudden everybody who did research in computer science, right, and did this network analysis, they started using that paper and that data set as a reference and citing it. So I don't think this paper originally within the community of sociologists had a very big impact, right? It was just one of the tons of papers published out there, and it's just became it was made famous by computer scientists because they just found it and somebody started it, and then it just like snowballed. So Google it. I'm sure you will instantly find the paper, and next time you'll tell us. All right, good. Anything else? All right, then we're done.